Hi, welcome once again. This time, let us look at the Common Test June 2012 paper. As a revision, we look at a long question, question 3. Now this question reads as follows. A. Figure 3.1 shows a parallel circuit comprising of R resistor, L inductors, and C capacitor elements with the following values. The incoming current is given as I phasor 0.2 amps, the angle of 0 phase angle, the frequency of 50 Hertz, and the resistor value is 330 ohm, inductor 600 millihenry, and finally the capacitor is 15 microfarad. Now the circuit is in parallel, which means that all the three elements can be drawn as follows: resistor, inductor L, and finally a capacitor C, all in parallel with the incoming current and the applied voltage E. Now, what does the question want us to find? First, determine the impedance of the load in polar form. Secondly, calculate the supply voltage E, and finally, determine the power factor of this load comprising of the capacitor, inductor, and the resistor. Well, let's begin. I've drawn roughly a little circuit like that, right? So the first thing to do is we want to find the total impedance ZT. Now we know from we've got impedance in parallel, 1 upon ZT is equals to 1 upon Z, the impedance due to the capacitor, plus the impedance due to the inductor, plus impedance due to the resistor. So in order to do the calculation, we have to determine the impedance of each of these elements separately. Now, if the frequency of the supply voltage is 50 Hz, then we know that the angular velocity 2 pi f is equals to 100 pi radians per second, or 314.16 radians per second. From here, then I can calculate the reactance due to the inductor, which is given by this formula omega L, which is equals to 314.16 multiplied by the inductor value, which is 0.6 Henry. That gives me a total impedance of 188.5 ohm. Right, next I calculate the reactance due to the capacitor, which is 1 upon omega C. That's 314.16 times 15 microfarad. That gives me 212.2 ohms. Right? So once I determine this, now because these are pure inductance and pure capacitance, I can say that they are equivalent to the impedance. Okay, so now I'm ready to substitute the values into this impedance in parallel kind of calculation. So using phasor version, I have XC. I can present it as 1 upon 212.2 with the angle of minus 90 degrees. Okay. Plus 1 upon 1885 with the angle of 90 degrees because it's an inductor. Plus 1 upon the resistance, so it should be 330 with the angle of 0 degrees. So this is the phasor, 1 upon phasor. Now 1 can be equals to, in phasor version, is 1 at an angle of 0 degrees. So if I were to calculate, 1 upon 212.2 will give me 4.7 125 90 degrees plus 5.305 minus 90 degrees, each multiplied by 10 minus 3, 10 minus 3 plus 3.03 an angle of 0 degree, also multiplied by 10 minus 3. Now I need to add complex numbers. So the quickest way for me is to convert them all to rectangular format. For this 90 degrees, so I will put plus J symbol in front of this number. So that gives me 4.712 times 10 to the minus 3. Here is minus 90, so it's minus J 5.305 times 10 to the minus 3 plus 3.03 and minus 3. That gives me, if I were to rearrange it into the rectangular, the normal way of rectangular format. Remember, rectangular format is R plus JX counting. So I will have 3.03 times 10 minus 3. This time, here is minus those parts, so the result gives me a minus J 0.5925 times 10 minus 3. That's approximately 3.03 times 10 minus 3 minus J 0.6 times 10 minus 3. Now I then convert this back to the polar format, which gives me 3.088 angle minus 11.2 degrees. Cos and the 10 minus 3, forgotten there's another 10 minus 3. Right, now this is 1 upon Z total. So in order to find total, Z total, I have to inverse this again. So I get 1 upon 3.088 times 10 to the minus 3 with the angle of minus 11.2 degrees. That gives me the final answer of 323.83, the angle of 11.2 ohms. Right, here you are. This is the first part, total impedance of the circuit given here.